All right, so 1-1 is a very, very, very introductory section, right? My goal today is to do 1-1 and 1-2 because we took a little bit of time on that. We might just get through 1-1, but that's fine. But it is introductory, but it's important still, right? We're going to talk about types of numbers and then really look at the first thing of quantification, thinking about the behavior of two numbers and how they relate to one another on a number line. So if we're talking about distances, if we're talking about comparing values, but again, the basics of what you're going to learn like a pre-algebra kind of thing. So we'll talk about number lines specifically, compare their values, and then talk about absolute value. Okay, let's go to the second slide, please. Oops, what happened there? There we go. In the second slide, what we're noticing here is our number sets and our subsets. So let's talk about this for a little while. First, what's a real number? We've talked about real numbers before. You've probably heard about the phrase rational and integer and whole and natural and irrational. You can see the way it's split. But why don't we talk about real numbers? What other kind of numbers are there besides real numbers? You may probably haven't even heard of this or seen it yet.
Imaginary numbers.
Yeah. So there are also a set of numbers called imaginary numbers, which we're going to really touch upon about halfway through the years when we start working with imaginary numbers. And imaginary numbers, just a little preview, are used widely. You know where they're used, isn't it?
The square root of negative numbers.
Yeah, the square roots of negative numbers. And they're utilized widely in engineering. You know, a lot of what's called loop and control systems use imaginary values. So this air conditioner that's running right now is on a feedback system. It says right now, what is the temperature set at? I can't even see from here, but say it says 68, I can't really see. If it's below 68, the air conditioner does what? If it gets below 68 in the room and it's supposed to be at 68, what does it do? Turns off. If it's hotter than 68 in the room, what does it do? Yeah, it's a thermostat, right? We understand a thermostat, but the inner workings of that are actually far more complex than simply on and off. There's a system that's always checking the temperature, and that system has a little controller box, and it's a simple robotics thing where your controller itself is telling it what to do, and it uses feedback. Imaginary numbers, what we're not getting into today, what we're going to get into, really has a big role in feedback systems. Okay, so when we get to that later in here, I want you to know that it's not just some arbitrary thing that mathematicians made up. It's very useful also. But today we're going to look at real numbers. Okay, so real numbers, for the sake of lack of a better phrase, are not imaginary numbers. Okay, the easy way to put it. All numbers that are not imaginary are real. It's an easy way to think about that. Now, the subsets of real numbers we can describe them. So what's the difference between rational and irrational? Two major categories of real numbers. Rational versus irrational. I'll tell you.
Rational are non-trivial. There's you can't find a pattern in it, and rational numbers have a pattern. There's numbers where you can math with.
Yeah, so you're thinking of the decimal interpretation, which is good. That works. So if you think about the decimal itself, right, the decimal and the values after the decimal, if there is no pattern to those values, well, then we have an irrational number. Okay, like for example, if I wrote down the square root of 2, if you type the square root of 2 in your calculator, which you should have with you today, right? Type in the square root of 2, you'll see that this value goes on forever with no predictable pattern whatsoever. The value you get on your calculator when you type in square root 2, it gives you a value that goes on and you're not going to find a pattern in it. Okay, for square root 2. So, as Althea said, if there's no pattern in the decimal, the number is irrational. There's another way to think about irrational numbers. And to think about them, we can think about really what rational numbers are. So who knows another interpretation of what a rational number is? And you were right with the way you said it. It has a decimal that terminates or has a pattern. But there's another way to express rational numbers. Very good, Nick. Any number that can be written as a fraction. Okay, a rational number is any number that can be written as a fraction. And that is true for all rational numbers. Even decimals that repeat infinitely, they can be written as a fraction. For example, 0.3333333333333, what is that? What fraction? 1/3, Olivia, very good, 1/3. So a repeating decimal or a fraction are automatically rational numbers. So I'll put examples: 2/3, 0.57 repeated. Those are both rational numbers. I don't know what this turns out to be as a fraction. I don't know off the top of my head, but I don't care. If there's a repeating bar somewhere, it's rational. Okay? If something about it repeats, it is rational. Also, decimals that terminate, right? What about 2.5? Why is the number 2.5 considered rational? I don't see a repeat. We just said it repeats, right? All rational numbers have a repeating decimal. I just said that, but I don't see anything repeating.
Because there's a fraction.
What does that become as a fraction?
2 and
Which as a fraction, improper fraction, what is that?
mixed number.
Yeah, so you gave 2.5 as a mixed number. What is it as an improper?
5/2.
5/2. Now, but I also want to point out, what number comes after the 2.5? What number is right here?
0.
How many times? Infinitely many. So when you see a terminating decimal, it's really like there's a 0 there with a bar over it. Right? Think about that for a second. I want you to understand this interpretation. If 0 goes on forever, well, that's your repeating part. So whenever you look for a value to see if it's rational versus irrational, if there's any repeated pattern to the decimal, or if that number can be written as a fraction, we know that it is rational. Fun fact, all square roots of non-perfect squares are irrational. All square roots of non-perfect squares. What is a non-perfect square? What am I saying?
It's not like perfect. Like if you put the numbers to try making a square would be perfect.
So give me an example of a perfect square.
16.
16. Give me another one.
25.
25. So any non-perfect, right? We get it now with 2 examples. Any non-perfect square. So root 2, root 3. Does root 4 work? No, because root 4 is really just 2. Right? Square root of 4 is 2. So all of these values, but make sure that you skip the perfect squares. Okay? I started on the right, I apologize. But I skipped the perfect squares, notice that? Now, what other type of number, or what other number that you know very well is irrational? Pi. Good. Everyone knows pi. Right? 3.1415296. I mean, it goes on and on and on, and it goes on forever. And there are computers literally calculating all the decimals of pi to this day still, and it will never, ever end. What is pi? What is it? Give me the definition of what pi actually is. I got you, Julian.
It's like circumference divided by diameter.
Yeah, that's well done. It is the ratio of a circumference divided by a circle's diameter. And it's amazing. Think about the beauty of nature. Every single circle that exists anywhere in the world, that is a perfect circle, not an ellipse, any circle that exists, you take the circumference, measure it, take the diameter, measure it, divide it, you always get pi. Isn't that amazing to think about? It's like the golden ratio. The golden ratio is another value that occurs in nature a lot. In symmetry, in spirals of like flower petals, in the shape of like a snail shell, shells when they actually spiral out, this golden ratio concept. There's another type of number like pi. Okay, so another value, lowercase e. And I don't know if anybody's heard of this yet, but lowercase e is called the natural base. We're going to learn about lowercase e later on in the Okay, it's another constant like pi. Pi is a constant. It's a value that does not change, again, defined as the ratio of circumference to diameter. That's what pi really is. You'll learn obviously more about pi and circles next year in geometry, but just giving you a little feedback because you've probably heard of it already in your 8th grade courses. On the left-hand side, let's take a look at the subsets of rational numbers. Integers. Integers are my first subset, the way this table or chart is shown. So what are integers? Who can tell me what integers are specifically? Jimmy, what do you got?
Whole numbers?
Whole numbers. Well, I see whole numbers are here, Jimmy, so they can't be the same, right? So what do you have to say? You're close.
They are any number without a decimal.
Okay, any number that doesn't have a decimal, I'm good with that, but give me more specifics. Another way of putting it.
And I thought it was like any number that's not negative.
No?
Any positive, negative, or 0 whole number?
Yes. Any whole number and its negatives. Because whole numbers, by definition, are actually 0, 1, 2, etc. It starts at 0. Integers are whole numbers, but also the negatives. So integers start all the way at negative infinity. I'm going to put negative 3, negative 2, negative 1, 0, 1, 2. I'll put dot, dot, dot on both sides. Is that fair to put that on both sides? To show that this extends to the left and extends to the right. Whereas whole number starts at 0 and it just keeps counting up. Anybody know what natural numbers, the difference? It's kind of ridiculous that we even have a name for it. I'm not going to quiz you on the difference of these two specifically because they're pretty much the same. Ina? Yeah, natural numbers, another word for it is the counting numbers. 1, 2, 3, 4. You don't start counting at 0 ever, right? If you were to count the amount of items in a room, you start at 1. Natural numbers start at 1. That's the only difference between natural and whole numbers. Okay? Easy way to remember it. Ready? First of all, what is a mnemonic device? Mnemonic device. What does that mean? God bless you.
It's kind of like a way to help you remember something.
Very good. I love mnemonic devices. Okay? Take a look. Whole numbers. What letter is in whole? O. What does O look like? And it's not a natural. If you confuse these two, because this one you should not forget. And the most common misconception is confusing these two. The 0 is the 0. There's no 0 there. Easy enough. Okay? Again, integers you got to know. Rational, irrational, you got to know. These two, they get a little bit, people mix them up. Let's go to the next. So we have our definitions. I'm not going to reiterate all the things we just said. So if you were a little bit behind on that slide and we're writing stuff down, on this next slide, what we're going to see here, and what we do see right now, is the definitions of those types of numbers written out. Okay, I'm going to press on to the next slide. Let's keep going. So now we're going to take a look at number lines. Take a look at number lines. So first of all, you've all seen a number line before. When you were a kid, in like kindergarten, you saw a number line. They were on the wall, right? On the wall, they always have an A, B, C, D, E, F, right? That's a number line, it's just a letter line. We've seen number lines, you start at 0, you start at negative infinity, but it's pretty much counting all of your integers. That's what's on a number line. We call the location that a value has on a number line, it's coordinate. Just like on the XY axis, it's a coordinate. But on the XY axis, we have how many coordinates that are given to define a point. On the XY axis, how many coordinates are you given? 2. You're given X and Y. So it's maybe 2, 3. On a number line, you only need one coordinate, one value, 2, or 5, or 7, etc., etc. A number line is a tool that can be useful when comparing the quantities of two values, when comparing which is greater than the other. Okay, so let's continue. Let's take a look at this first example. It says, find the coordinate of the point 2/3 of the way from A to B for the number line shown below. Find the coordinate of the point 2/3 of the way from A to B. Now, there are two ways to approach this. There's a simple way, which I would probably take for this one, and a more complicated way, which we'll use in a minute on a harder problem that needs it. So what's the easy way to solve a problem like this? What's the easy way? Give me the beginning part.
Just count.
Yeah, just count, right? I mean, physically just count. So we count, we recognize here that there are 6 spaces between here. So that's my gap. My gap is 6, right? Between -2 and 4. Obviously, if I ever want to know the difference between two numbers, I could subtract them. Take the larger number, 4, minus -2. 4 minus -2 is equal to 6. That's my gap. Now, what is 2/3 of 6? What is 2/3 of 6?
4.
It is 4. But am I going 4 away from A or 4 away from B? This is where word problems get a little bit tricky and students struggle sometimes. What do you think, John?
4 away from A.
Why?
Because it's asking find the coordinate point 2/3 away from A to B.
Good. So it means start at A and go 4 values to the right toward B. And we stop right here. Okay, very good, John. Good explanation. I underline what John was talking about. Word problems are not any more difficult than you make them. Now, dissecting them becomes a skill over time. We're going to do a lot of stuff with word problems in this class. You're going to recognize that we want to break things into components. So the piece that I underlined, 2/3 of the way from A to B, that triggered the thought in my mind to say, from A to B, start at A and go 2/3, just as Gus told us, which is 4 units to the right. And there's my spot. Okay, from A to B. From A to B. All right, let's go to the next example. Please raise your hand and ask, or just ask a question if you're not sure. Okay, please ask a question if you're not certain on something. Now, this is where it gets a lot more confusing. This is where it gets a lot more confusing. Now it says, on the number line shown, determine the coordinates that are half as far from A as from B. Before we even think about the answer, are these coordinates going to be closer to A or closer to B? Are they closer to A or are they closer to B, Nick? No, they're not equal distant. They're not equal distance. I would say if it would have said midpoint or equivalent between. You're seeing half and you're thinking halfway between. but it doesn't say halfway between, does it? Careful, read it again. John, what do you think?
Closer to B.
Closer to B? Why would you say closer to B, John?
Because on the number line it shows they're asking half of the distance between A and B from B.
It's not. I understand where you're seeing that, but it's not that what it is. Get out there.
A, because the A is half the distance from B. If the A is closer, then it's only half.
You're right that it's A, but your explanation is not clear.
It's A because it says half as far from A as from B. So it's going to be closer to B, split up into fourths.
So, thirds. So if we look at this, this is the key. Half as far from A as from B. So if a value is 6 units from B, it would be half as far from A, which is 3. Again, if a value is 10 units away from B, it will be half as far from A, which is 5. So the value we're looking for is going to be closer to A. So I'm going to put a little, like if this were my halfway point, which it is, right, there's my halfway point, it's going to be somewhere over here. It's going to be closer to A than it is from B. Again, it's half as far from A as it is from B. Now, you can guess and check, obviously, right? You can try these integer values, or you can recognize, well, if it's half as far as... John? No. Sean?
Yes.
Okay. As Sean mentioned a moment ago, we're going to split this into thirds, really. It's thirds we're going to break it into, because if I'm the point in the middle, and I'm 10 away from B, and only 5 from A, I've got a 5 jump, another jump of 5, and another jump of 5. See how it works out to be thirds, really? So when I do this problem, I want whatever this distance is over here to be half of whatever this distance is over here. So let me take that midpoint line I drew, okay? Let me take that midpoint line and move it over 1 unit first. Does that work? What's this gap right here, and what's this gap right here? So that works, right? So -3 is definitely my answer. Again, -3 is definitely my answer. Now, here's the thing though. There's another answer. There's a second point that this works true for. Enid, you start to see where would that point be, Enid? I saw you go, yeah. So give me, not -1. That would be half as far from B as from A. I like the way you thought about that though. She was thinking like just reverse the two. I'm saying there is another answer, another coordinate that is half as far from A as it is from B. Again, we want this point to be closer to A than it is to B. Where do you think it might occur, John? Where do you think? Well, -4, let's do it. What's the gap here, John?
Oh,
And what's the gap over here then, though? So this is 1/5 of the gap than this is, right? We want it to be half. That doesn't work. But I like the idea. Think outside the box. It most likely will be a fraction. It may be a fraction on a whole number, so you're on the right track, but I want more than just that. Where will this number, I don't want the answer, but generally, where will this answer lie? Is it going to be over here, over here, over here, over here, over here? Where is it going to be on the number line?
Off the number line.
Off the number line that we see. That's why I said think outside the box. Extend your negative number line a little bit. It's going to be somewhere over here. Think about a point over here. I'm going to put an X for now. Okay, I'm going to put an X. Isn't that X closer to A than it is to B? And there's a point, if I keep moving out, where it will be half as far from A as it is from B. You got the point? -8. -8 from -5 is 3 units away. And -8 from +1 is going to be 9 units away. So that's going to be 3 units away, and that's 9. That's a third. But you're on the right track. I like the way you're thinking this.
Yeah, I messed up.
It's okay.
Instead of saying -8
That's all right.
distance from 1, I put -5.
Now, can we, before we guess and check anymore, can we think and recognize that this is algebra? So let's use an algebraic approach. How do I find the distance between 2 points on a number line? What operation do I use to find the distance between 2 points on a number line? What's the distance between 8 and 5? Subtraction, right? That's the algorithm we use, subtraction. Agreed? So, let's think about this for now. What can I write as the distance from A to the unknown point? How do I figure out the distance between these two? this value minus, go ahead. What are you going to call this? X. And what is the value of A? Negative 5. So the distance between the point A and the unknown is really equal to negative 5 minus X. I'm using subscripts for distance here, so the distance between point A and the unknown X is really derived by taking the larger number, which is A, negative 5, subtracting the smaller value, which is the unknown X. That's the distance. What is the distance between B and X? How do I find the distance between the point B and the unknown X? Again, use the same operation. Del Franco, go ahead. 1 minus X. Again, the distance between this value B right here, I'm going to point actually so you can see it better later. The distance between this value B and all the way out here at X is going to be whatever B is minus X, and that's that value.
Oh, new system of equation.
We don't even need a system actually. We can just use a proportion. Why can I use a proportion? What do I know about the relative gaps? What are we told in the problem? It's half as far from A, isn't it? So the distance from A to X should be half of this. Agreed? So watch what I'm going to do. I'm going to say, well, if I took the distance from A to X and the distance from B to X, that should reduce to 1/2. Give me one more second. So I take negative 5 minus X over 1 minus X, set it equal to 1/2, and go ahead and solve this. Okay? Just see what I want to leave you off with. Okay, so here's what I need you to do tonight. Listen carefully. Listen carefully. I would like you to fill in the next 3-4 slides by watching tonight under Mr. Howell's videos. You're going to see that I have a video for section 1.1, and we left off on example 2. You could finish solving this on your own. You can start packing up. You could finish solving this on your own, and then go on to the next slide about inequalities and number lines. Listen to the video that I've already recorded under Mr. Howell's videos. The rest of it, you can skip ahead, and just finish these last couple slides. Do the homework tonight. Just 1.1 though. You don't need to do section 1.2. We didn't get to it yet. On Moodle it says to do 1.2 tonight. I'll change that obviously, okay? So this is your homework for 1.1 after you finish the last 3 slides.
So it will be problems 3 to 39?
Yep, it's exactly what you see here. And then read page 26. That's all I want you to do. This is out of your textbook. All of your homework is always out of your textbooks. WE stands for written exercises. There are oral exercises and written exercises in the book. If you try to do the oral exercises, there's only like 5 of them. You're clearly going to run out. It's supposed to be 39, right? So pick up on that tonight. Get moving, guys. Multiples of 3. Sorry, multiples of 3.
Shall we do
3, 6, 9, 12, 15, 18, 21, 24, 27.
So it's a lot less than 3.
Yes, guys, it's a lot fewer than this many problems, right? Multiples of 3, multiples of 3. 3, 6, instead of writing it all out, yeah?
Do you want us to hand it in or send it?
If you do it in Notability, send it right to Drive, but put the right, call it 1.1, homework, or label it the right way, yeah. If you do a hard copy, just bring it in tomorrow, okay? Guys, have a good day. Get moving now. We have another class. I don't want you to late. Get moving.
Wait, do you guys know our Christian services?
Kelly again.
Alright.
Who's your teacher for that?
It's
Miss Faber? Okay. If she, for some reason, gets upset that you're a minute late, let her know you're still hold on over math, okay?